Okay, welcome to class. We've got 10-8, last new section of information. Keep in mind, tomorrow's a review, and I could give the test as early as Friday. I'm planning to do it Tuesday, but I really need you to participate with what's happening today and make sure you're focused and getting stuff done. And those extra days are there to be successful. Monday, I will, however, start chapter 11 because I will be done with all material I need to do for the test. I'm just not giving a Monday test because I've seen them and they never are good. Okay, because people don't remember, they forget, and it's better for us to do a Tuesday test after I've done new material on a Monday. And you guys will have an idea of what it's like to be a college student at that time too, because they test in one spot, but they keep going. They just keep going until the end of the semester, and they test at certain times. So you'll get used to this. Today's objective is to use segment and area models to find the probability of events. So we're talking about probability, okay? Bloom has kind of a soapbox about this. So when we're doing probabilities based on lengths and areas, I want to make sure that you recognize we're just looking for probabilities of lengths and areas. You guys will eventually be 18 and legally able to gamble. I want you to know that gambling is a pastime, not necessarily a job title for what you should do for life. Okay, if you're that good, you will be barred by casinos because they're going to feel that you're taking advantage of them. Isn't that interesting? When you get really good at taking their money, they say you can't play here no more. But if you get really bad at giving them money, they're more happy to take your money and to let you go bankrupt because you're willing to give that money to them. It should be a quid pro quo. If it's good for the goose, good for the gander, right? But it doesn't work that way for them. If you start winning a lot of money from them, you can't play here no more. Our money, we want to keep it. And remember, casinos are here to be businesses. They are money-making institutions. They are not charitable organizations existing to give you money because they're going to take your money. And when they give you too much money because you're winning, they bar you from play. People are like, what? Yeah, that's what's going on. So Bloom's rule of gambling. If you're not willing to put the money you're going to gamble with up on a table and walk away in a crowded lunchroom and not worry about whatever the money is, then you don't gamble with anything more than that. My rule of thumb is $1. Okay, I don't know what yours would be. If I got $1, hey man, that's almost a coffee. All right, I don't want to throw a coffee up on the table unless I'm drinking it and it's empty. All right, so you got to keep in mind that's your risk aversion formula from Mr. Bloom. Quite frankly, if you want to take out the money you're going to bring to a casino and you can just place it on the table and turn and walk, then go for it. Okay, whatever that money is. Notice how general that is. Okay. But remember, if you would invest that money at, well, I don't know, 10, 15% interest, and people, where do you get that? Stock market, historic average. Doesn't matter who's present, by the way. Historic average, stock market. Your return, you'd be in 30 years, 30, 40 years, you'd be a millionaire at $200 a month. Okay, so just keep that in mind. That's pretty much the average that people go to the casino with. But little side note. I'm going to start class now, but it's all about probability. And by the way, one other side note, when you start saving for your retirement, pay yourself like you're a bill, okay? You should have something coming out of your savings automatically going to your investments, 401k, Roth IRA, whatever it is, to take care of you in your future, okay? The sooner the better, because time is on your side up until you're about 25, 30, and then all of a sudden you're working like everybody else to try to get that money accumulated. Time value of money is really a cool little thing. If you learn anything out of that, learn that. Now, here's the deal. Today, talking about probability of event is the probability of an event is likelihood that the event will happen. Okay, now I've got over here on the board, won't happen, 0. Okay, monkeys flying out of your butt. Although we have seen it in the movie, so it could happen, but it's only because of animatronics. Okay, will happen for sure, sun will rise the next day. Okay, I can guarantee the sun will be up. And some people, what if it explodes? Then we won't be here to tell me I'm wrong, will you? Okay. The next thing we're looking at is thinking about the other side of probability. People are like, the other side? When a weather person says, hey, it's 70% chance of rain, what's the probability it won't rain? 30%. You take 100, subtract 70, you get the probability of something that won't happen. Okay, so there's a kinship there, so we're going to be working with that today too. As we're going through, make sure you recognize probability is all about us looking at area of event that we want to have happen out of the total ways events can happen. So now, theoretical probability. Theoretical probability is something that, you know, like if I flip a coin, I wonder if I still have that coin. Somebody could have stolen it, right? If I flip a coin, what's the probability that it's a heads or a tails? Oh, I've lost it for sure now. It's in much, you can keep that much. I gave you a tip today. Okay, but here's the deal. What's the probability that it's heads? 50%. What's the probability that it's tails? Weird, right? But I have people out there, what's your favorite one to pick when you're flipping a coin, heads or tails? I've got heads here, I got tails over there. The idea of the law of large numbers, it has a statement in this, because theoretical probability allows the idea that all events are equally likely to occur. Experimental probability, you actually run trials of an experiment. You've done the coin flipping one, I know that. You know, between 4th grade and now, you flip coins and tally of heads and tails, okay? That's an experimental probability. The idea of law of large numbers. The more often something happens, the more likely your results will converge to be the theoretical results. Okay, some people might, oh yeah, well, every time I flip a coin, it's always 75% heads. Well, you flipped it 4 times and 3 heads came up. Fantastic. You flip it 400 times, and I don't think it'll be 300 out of 400. Okay, the law of large numbers will take over and it'll approximate 50%, your experimental probability. Now, keeping in mind as we go through here, we have the opportunity to recognize that probability of event, number of favorable outcomes, number of possible outcomes, total is what we're going to divide by. Probability can be expressed as a fraction, 1/2, a decimal, 0.5, and percent, 50%. And all I want you to do in problem 1 is convert from decimals and fractions to percent. And all you're doing is dividing if you have it a fraction. And if you're here, like an A, I'm just asking you to move it 2 places to the right. So 0.5, we said 50%. So do the other 3 quite quickly, please. I got 82%, I got myself a 40%, and I got myself a 35%. How are you doing with these? Are we all right? I know some people are, really? You're making us change over from decimal to percent and back and forth. We should know this pretty well. I just review it just in case you forgot. Now, geometric probability of event is a ratio that involves geometric measures such as length or area. Probability of length. This is kind of freaks people out. It's not that bad. What we're doing is, I want to know what the probability, and I'm reading the problem, and this is how you read this. The probability that S is on segment BC, okay? Very descriptive probability statement there. So that's BC, the red, BC, it's going to land in BC. All along, it could land A through D. So I'm betting it's going to land BC. If I can bet that, what's the probability? If it's going to land on AD, that it is in the BC area, okay? So point S on segment AD is chosen at random. Probability that S is on segment BC is the ratio of length of segment BC to the length of segment AD, and that's what this does. That's all it is, and we're going to practice that next. Now, point K is on segment ST is chosen at random, okay? I can't emphasize this random occurrence thing enough, okay, as we talk about these. What is the probability that K lies on segment QR? Now, segment QR first, is from 5 to 8. I know QR is 3 big. Are you okay that this distance from Q to R is 3? Do you see it? Some people, well, yeah, I can count on from 5, 6, 7, 8. That's 3 Bloom. Or 8 minus 5, it's 3. Okay? Now, the total possible places it could land is on ST. And ST is 14 minus 2. ST is 12. Okay? Those are my two values. I need to find those. Okay? Enabled for me to establish my probability. So now QR divided by ST. 3 divided by 12, I'd reduce 1/4. 1/4 becomes a fraction, is a fraction that can become a decimal, 0.25 or 25%. Are we okay with this? Now again, what's the probability it ain't gonna land on QR? 75%. Okay, just go ahead and talk to your English teachers about my poor English about using the word ain't. Okay, your turn. You guys are doing number 2. See if you gets it. Go. Please be here. Don't be doing this. Okay. Thank you. Make sure you're present. Make sure you're focused on what we're doing for the day. If you're splitting your attentions, you aren't learning stuff that we're actually doing today. Studies have shown. Now, SR. SR on our little number line on top. SR is 8 minus 2, which is 6. Okay. ST is still the same. Some people are like, how did he get 8 minus 2? S is 2, R is 8, 8 minus 2 is 6. That's where I get it. Okay. Now, 12, still S. That's a half, so that's 50%. So we're golden, right? This is totally working. And now we get the opportunity. We did, or I did, then kind of we did. Now it's a you do. Okay. Now, on this next one, I have people who shortcut stuff. They just give me numbers. Studies have shown that if you actually are going to review for a test, a quiz, or even if you're taking a quiz and you have your notes available, show the work. It's not about the fact that you can't come up with the number. It's about how did you come up with the number. When you reread your notes, it shouldn't be a refiguring of your notes. It should be, oh, that's how I did that. Okay, I can do that. So I've got the segment AB. I'm going to land on segment AB. And AB is from 6 to 3. That's 3. AD is 7. So I got a 3 in 7 chance. Okay. Leave them as fractions. Do the other 3. Show your work. Get it going. Go. Trying to kill me. Yeah. Yeah, you can divide that and it'll be about 0.43, 43%. Okay, but I'm just going to leave them as fractions because once you get the fraction, I can ask you to leave it as a number between 0 and 1. I can use it as a percent between 0 and 100, okay, or something to that extent, or just as the fraction itself. Now in AC, AC's difference is 6. So that's 6 over 7. And then I've got BD. And notice I'm looking for a probability T is on segment BD. I'm looking for a probability T is on segment BC. All right. So that way it's descriptive. It's like, oh yeah, that's what we found. Okay. When you reread, you get what we put in, the event of interest, the segment I want to land on of the total event. So you get to review that for that length idea. Okay. The probability of length. Now, BD out of AD, BC out of AD. These should be our values right at this point. Are there any questions on A, B, C, or D, or how I did stuff or got them done? Folks, it's on your test. I guarantee it. Okay? So what I'm asking you is if you were taking the test today, would you be asking me questions? Because I got news for you. I wouldn't answer them on test day. I'll answer them now. And I was pretty clear about it, showing your work. I expect to see that work on the test. Okay? Presentation issues if you don't. Now, I got this set up as a number line from 0 to 25. I counted by 5. So I just wanted you to get a visual about this problem. And the problem states a commuter train runs every 25 minutes. So at 0, the train just left. I didn't catch it. I got to wait a full 25 minutes to the next train. Okay, and then the next person who comes in gets there just in time, misses that train. Okay. If a commuter arrives at the station at a random time, what's the probability that the commuter will have to wait at least 10 minutes? Now, that's not like 9 minutes, at least 10 or more. So I'm thinking that they arrived right here at time 0. It was the earliest they could arrive and waited full 25 minutes, because that's at least 10. Or they could have arrived right at 15 minutes before the train, because that is definitely 10, but it still fits in that area of at least. So if they arrive sometime between time 0 when the train left and 15 minutes later, what's the probability they're going to have to wait at least 10 minutes? Well, if they do that, it's going to be 15 out of the 25. I'm interested in them arriving in that 15-minute window that'll be at least 10 minutes. Okay? Now that's 60%. If they arrive in that window 10 minutes before the train arrives, they had a 40% chance of doing it, but that's a 60% chance if you want to look at it that way. This is 60. Okay? Now it's your turn. It's your turn. I don't know why I have that sitting there. Go for it. Check out B. Check out B. Check out B. Make sure you show the information. Make sure you kind of put in that number line so you have a visual description of what's going on. So we explain ourselves, can explain that problem to ourselves. Things will be good. You okay that if I'm going to wait 5 minutes, I'm in that, that's why I did that. It wasn't there. 5 out of 25. Okay, no more than 5 minutes. 5 minutes or less. No more than 5. 5's the most I'll wait, which means they're going to arrive in the 5-minute time window before they catch the train. Much like what you guys arrive at for catching your bus in the morning, unless your bus driver is not very predictable. Then you have to adjust your time window, because you could wait for as much as 15 minutes for the bus driver, or just 1 minute coming out at the same time every day, depending on traffic, depending on weather, and whether they got up in time or not. Okay, does that make sense? Questions about 4A or 4B. Now, those are probabilities of measure, of length, okay? We have been working really hard about talking about probability of area. Probability of area. Point S is in the region R, is chosen at random. The probability that S is in the region N, and region N over here is this yellow triangle, okay? And R is the whole area it could land in, okay? So if I'm looking at this, this is my solution. So the probability that S is in region N is the ratio of the area of region N to the area of region R. It's a ratio. Event of interest out of the total ways it could happen. Total ways it could happen. Okay? Giant ripping off the classroom. There's 32 people in here today. Okay? Peels back the wall, the ceiling, picks our classroom and just mixes us up. Okay? What's the probability that they pick you out? And they're just going to pick out one. 1 out of 32. Event of non-interest. I prefer not to be picked out by the giant. And we'll see where that goes with that probability. Event of interest out of the total ways it could happen. So here's the deal. On this one, I'm looking at my probability of shaded. I'm going to get rid of that too. I have my cave drawings up there. I've got a square minus circle. If I take the circle cut out of the square, I have them little yellow dog ears, okay? And they're saying, hey, a circle's inscribed in a square. Point Q in the square is chosen at random. What is the probability that Q lies in the shaded region? Well, think about it. If it's going to lie in the shaded region, these little dog-ear spots around my square, I've got to take away the circle from the square to find out what area is left over. That's why we take square minus circle. But the whole area that my dart or point could land in is in the square. So I have a probability of that region, and I have my equations that I'm going to use. I have my square equation, side squared, minus pi r squared, my circle equation, all over side squared. So now let's start talking about what that is as I go. So I got the probability I land shaded. Probability I'm landing shaded. Wow, Bloom, these are area formulas that we've been working really hard. We've done circles, we've done rectangles, we've done squares, we've done parallelograms, we've done trapezoids, we've done polygons that are regular size, same interior angle value, same exterior sides. We know how to find all those areas now. At least I hope you do. Because 10.8, the application of finding the area of interest over the total area you can land in, covers all of them. Okay? So, once I get this, I just pop it in my calculator and evaluate. Now, this is my probability that I'm going to land in the shaded region, and that shaded region is those little dog ears in my triangle. I shouldn't say the triangle, but in the corners of my square, right? What's the probability it won't land there? Anybody got the probability it won't land in the shaded region? How did you do that? 78.5, how did you do that? You rounded a little? How did you go from 21.5 and got 78, so how did you do that? No, I'm not saying you were, I'm just wondering how did you come up with it? That's what I wanted to hear. You subtracted the percent where it lands shaded to get the percent that it wouldn't land shaded. Okay, your turn, do be. I'm going to give you the cave drawing, give you an idea about what's going on there. Okay, thank you, you too. Okay. Miss Schaff, where are you hiding here? Schaff. Okay, go ahead, get this one done. Like, take attendance. Shoot. I put it in my calculator. So this is put the stuff on top, hit enter, divide by the stuff on the bottom. Okay. So just as a review on stuff, because of the questions were being asked, when I have this set up, keep in mind that this is a fraction bar. It tells me to do all this on top, and then hit enter, and then divide by the stuff on the bottom, and I should get 0.215. Make sure you keep focused on the fact, not only is this me teaching you about the stuff we're learning about today, but more so calculator functionality and how to use it, order of operations, review to make sure that you're successful in your quizzes and tests. Okay, so we got a probability of shaded. We're going to take the square minus the triangle. And this one's kind of unique because it doesn't really look at it like it in a way for some people, but really it's 50% because I've got the area of the square is 25 and the area of the triangle is half of that, 12.5. Well, it should be 50%, okay, as we go through. But this is how we came about it. Okay, and I got some people going, wow, he did a lot of stuff. I just wanted to make sure that people saw where all my numbers came from on this. Okay, if you went from this step to that step, I'm okay. I'm okay with that. I look for the numbers you plugged in. I'm looking for the formulas. I'm looking for the probability you're finding. I expect you to be able to organize it so it's easy for me to grade, because if it's hidden, it'll be more wrong than right. If I've got to search for your solution, that is not how we do quizzes and tests. It shouldn't be, oh, I pulled the fast one on Bloom. The answers on each problem are on the back of the sheet that those problems are on. Well, dude, I'll just mark it all zeros. Your job during a quiz and test is to present your knowledge of the material and how you find the solution. It's not a circus act that I get to follow and figure out what they do, okay? Now, I'm skipping problem 6. In 7, we are working with a hexagon and a circle, and I've got the probability. I've got to find the hexagon area and I got to find the circle area. I have provided information for those two shapes. I'm going to use that equilateral triangle times 6 for the hexagon. The side length is 10.4, so that's what I'm plugging in. And the radius of the circle is 9. That was found because this whole thing is 18 and half of it's 9. That's also how I could find the apothem of the hexagon if I wanted to use the apothem, 1/2 ANS. But I pop that in too. So now find your finals and don't round your intermediate answers. And people are like, well, Bloom, what? Well, think about what we're doing. We got it exact answers. That one's 281.00. That one came out really nice. But this one's going to be 81 pi. Okay? So I'm going to find probability it's going to land shaded. Circle divided by hexagon. Go for it. Circle divided by hexagon. Okay? After you do circle divided by hexagon, please, 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 please find the answer for B. We've already done it a couple times. I just want to make sure you gets it. So we have 81 pi over 281. Are you okay with that? And now I have the probability to land in the shaded region. That shaded region is pretty huge, right? So it should be a pretty big probability. Okay. Now, what's the probability for me to land in the non-shaded region? Okay. I could take the information we just collected, with the area of the shapes and do it this way. So that's probability it's going to land in the unshaded region right here, so I can actually get that going. Or I could do it this way. Check it out. Where did I get that 0.9056? 0.9056, excuse me, came from our answer. That's when it's probability that's going to land shaded. The probability it's going to land unshaded is right here. 0.0944 or 9.44%. Okay, that's the easier way to do it. I'm gonna be honest, but I want you to make that connection because on SAT, ACT, MCA, they ask that crazy question. They give you a probability of an event that happened, and then they want to give them the probability it didn't, and you subtract it from 1 or subtract it from 100. I've seen it. Yeah, but I've seen that question. I'm not saying that it's fair. It's just, oh, cool. Okay, I'm the MCA. Practice MCAs have it often. Okay, now, your turn. Go. Probability-wise. Now, keep in mind, when people see these pictures, it's the picture that freaks them out because, oh, I haven't seen that before. Holy cow, how do I do that? I kind of gave you some information, but I want you to be aware about something. Isn't that a whole circle? Right? That's the whole circle. Well, if I take that whole circle and I put it back in there, and I put it back in there this way, it actually takes up, oh, wait a minute, that's kind of like the one we just did. We did a hexagon minus the circle. Shouldn't we do a square minus the circle? Although the circle was split up funkily, if that's a word. I'm gonna have to try it on, password next time I, Words with Friends or Scrabble, funkily, see if they let me get away with that. But here's the deal. It's just a circle. I split it up differently. The area that's left, whether it's the whole circle or the halves the way we have it, would be the same. I'm doing my caveman drawing. Go for it. Get it done. See how you do. Remember, you're looking for probability that we are landing in the shaded region. And then I want you to find the probability it is not the shaded region we land in. And I want you to get into practice the habit. Once you find the one, you can use that to subtract from 1 or 100 to find the other. Again, calculator function, being able to plug in the correct values in your calculator to achieve the answer is a necessity. If you're having difficulty coming up with 0.2146, please talk to Bloom, okay? Or try re-entering your calculator stuff again. Everything on the top of the fraction bar should be evaluated and set, and you should hit enter. Then everything on the bottom, and then you divide them together, okay? Just make sure you're careful about your calculator use. And on this one, probability is not shaded. Could do that, or I could just do that. And I'm gonna be honest, I would do this one. That's the one I'm gonna do. It's 78.54. That's what's gonna happen. If I just divided it out, it would still come out, pi over 4, but I would totally do the red version. I wouldn't do the other. I just did the other just to make sure you know that both work. But remember, SAT, ACT, MCA, we have to learn skills, methods to be more efficient, to use our time better, so that we can have time to do the harder ones we hadn't anticipated on seeing. That's notes for today. Hopefully everything's going well. If it's not, there is before and after school help times. Make sure you're getting in to use them.